It's incredible how fast AI, especially these large language models, is advancing.
It really is. Almost hard to keep up sometimes.
But it always feels like there's a catch, right?
Right.
You hear about these amazing new capabilities,
Mm.
and then you realize they need like a massive data center and tons of power.
Yeah, the resource cost is just huge. It's this constant battle between, cutting edge AI and the practical limits, memory, energy, speed.
Attention, yeah. Getting it to actually work in the real world.
That fundamental tension is really at the heart of trying to make advanced AI practical. The potential is immense, but bridging that gap, that's the hurdle.
Okay, let's unpack this because today we're diving into something that could be a real game changer in that struggle. Maybe a shortcut.
A potential shortcut, yeah.
Oh.
Too powerful AI without those, well, insane resource demands.
They're talking about BitNet b1.58 2b4t.
Exactly. BitNet b1.58 2b4t. It's a really fascinating development.
But what is it, fundamentally?
It's the first open source large language model that's natively 1 bit at a pretty substantial scale, 2 billion parameters.
Natively 1 bit.
And trained on a huge data set, 4 trillion tokens.
Wow. Okay, a native 1-bit model with that many parameters, that almost sounds like it shouldn't work.
Right. It pushes the boundaries.
So our mission today really is to get under the hood. Understand how this thing manages to perform like the big full precision models.
But using way less computational power.
Yeah, finding a super efficient engine for a race car.
That's a good analogy. And for you listening, if you want to quickly grasp these breakthroughs without getting totally bogged down in jargon.
Which is always the goal here.
Exactly. This deep dive will focus on the core ideas that make BitNet b1.58 2b4t tick, make it so efficient, and what it could actually mean.
And we're basing this on
the technical report straight from arcsav.org. It lays out how they built it and tested it.
Great. So let's start with the why. Why build this? What's the big problem BitNet b1.58 2b4t is trying to solve?
Well, the main thing, as we touched on, is just the sheer amount of computational resources needed for today's best open LLMs.
The deployment costs.
Exactly. Memory, energy, latency, response time. It makes them impractical for a lot of real-world uses.
Like on your phone or in places without massive cloud access?
Precisely. Think edge devices or scenarios needing instant responses without relying on a huge server farm.
Right. It's like having this super brain locked in an energy-guzzling box. So how does this 1-bit idea even start to fix that?
So think of 1-bit LLMs as like extreme model optimization. It's a kind of quantization.
Quantization, like compressing the model.
Yeah, but taking it really far. The models weights the parameters that store its knowledge, and sometimes the activations, too.
The signals flowing through.
Right. They get drastically simplified. In this case, basically down to just 3 possible values, -1, 0, or +1.
Just 3 values instead of, like, regular numbers.
Instead of the usual 16-bit or 32-bit floating point numbers, yeah. This extreme reduction has potentially massive benefits.
Like needing way less storage space, I guess.
Exactly. Huge reduction in memory needed. If your model's parameters are just -1, 0, or +1, the model file size shrinks dramatically.
Which is great for smaller devices.
Critical for devices with limited RAM, but it's not just memory. Calculations with these simple values are also much less complex.
So faster and less power.
Potentially much faster inference, yes, and lower energy consumption. The math just gets simpler.
Okay, the 1-bit concept sounds great in theory. But you said previous attempts had issues. What went wrong before?
Well, the big challenge has always been keeping the performance up.
The trade-off.
Right. If you just take a normal pre-trained model and try to crush its weights down to 1 bit afterwards post-training quantization.
You lose accuracy.
Usually, yeah. You often see a significant drop in how well the model performs tasks. On the flip side, models trained from scratch as 1 bit.
Native 1-bit models.
Those tended to be smaller, maybe less complex, and just couldn't quite match the abilities of the bigger full precision guys.
So they were efficient, but not as smart.
Pretty much. BitNet b1.58 2b4t is trying to break that mold train, a native 1-bit model at a bigger scale, 2 billion parameters, and actually keep the performance high.
And the secret sauce seems to be in the architecture, these bitlinear layers. What's special about them?
The bitlinear layer is really the core innovation. It replaces the standard linear layers you find in transformers.
Okay.
And inside these layers, they do the weight quantization using a specific method called absmean quantization.
Absmear.
Yeah, it effectively takes the original weights and maps them onto those 3 values, -1, 0, +1. That's the 1.58-bit part, technically ternary.
Why 1.58? not just 1 bit.
Well, representing 3 states, -1, 0, +1, requires slightly more than 1 bit of information, technically log base 2 of 3, which is about 1.58 bits, so b1.58.
Oh, okay. Makes sense. And this dramatically shrinks the model size.
Dramatically,
Mhm.
and enables those super efficient math operations we talked about. It's like shrinking a library to a pamphlet, but keeping the key facts.
Okay, so weights are ternary, 1.58 bit. What about the activations? The data flowing through, are they also 1 bit?
No, the activations are quantized too, but less aggressively. They use 8-bit integers.
8-bit, okay.
Using a method called absmax, per token quantization. So it's still a reduction from full precision, but not as extreme as the weights.
And they needed something to keep it stable during training.
Yeah, training with this much quantization can be tricky. So they use something called sublin normalization to help with stability.
Interesting. And I see some other choices here. ReLU2 instead of SWIGLU. No bias terms. Why those?
Good catch.
Yeah.
The ReLU2 activation function, instead of the more common SWIGLU, seemed to encourage more sparsity in the network within this 1-bit context.
Sparsity meaning more zeros, more off switches.
Kind of, yeah, which can lead to more efficient computation down the line. And removing the bias terms.
Like LLM did.
Exactly, like Llama. It just helps trim down the total parameter count slightly and might simplify the quantization process a bit. Small gains add up.
And row P for positions.
Yep. Rotary position embeddings, ROPE. That's pretty standard now, a good way to encode word order information.
And the tokenizer, Llama A3s. That seems practical.
Definitely. Using the LLM-A3 tokenizer, which is a byte-level BPE, means it handles a wide variety of text and code well. Plus, it boosts compatibility with existing tools built around Llama. Makes it easier for people to adopt.
Okay, architecture nailed down. Now the training. 4 trillion tokens. How on earth do they manage that?
It was a carefully planned 3-phase process.
3 phases.
First, pre-training, then supervised fine-tuning, or SFT, and finally, direct preference optimization, DPO.
Let's start with pre-training. What were the key things there? Learning the basics.
Exactly. Giving the model a broad understanding of language, knowledge, reasoning. They used a cool 2-stage learning rate schedule.
2 stages. How did that work?
Stage 1 started with a relatively high learning rate, decaying with a cosine schedule. Apparently, these 1-bit models are more stable during training.
So they could push it harder at the start.
Seems so. Allows for a more aggressive initial learning phase. Then, about halfway through, they hit stage 2, the cool down phase.
Cool down.
Yeah, they dropped the learning rate significantly, but still used a cosine schedule. The idea was to let the model refine its knowledge using potentially higher quality data in the second half.
Interesting. So the training dynamics are different for 1 bit.
They really seem to be. It allows for these tailored strategies.
And the weight decay also had 2 stages.
It did. In the first stage, weight decay also followed a cosine schedule, peaking at 0.1. This helps prevent overfitting, especially with that high initial learning rate.
Standard practice, mostly.
Right, but then in the second stage, they just turned weight decay off completely, set it to 0.
Why?
The thinking is that with the lower learning rate and maybe better data, you want the model's parameters to settle into a really precise optimum without the constraint of weight decay pushing them towards 0. Let it fine-tune properly.
Okay. And the data itself for pre-training, what do they feed it?
A big mix. Lots of web crawls like DCLM, educational stuff from FineWeb EDU, standard large-scale text and code.
Anything special?
They specifically added synthetic math data to boost its reasoning capabilities, and they aligned the data presentation with the 2 stages.
Ow.
More general web data in the first, high learning rate stage, then focusing more on curated, perhaps higher quality data during that second cool down stage.
Smart. Okay, phase 1 done. Pre-training complete.
Yeah.
Then supervised fine-tuning, SFT. What's the goal there?
SFT is all about teaching the model to follow instructions better and be more helpful in conversations, making it more useful, basically.
Right, aligning it. What kind of data for that?
A whole bunch of public instruction following and conversational data sets. Things like Wild Chat, LMSYS, Chat1M, WizardLM, Evil Instruct, SlimOrca.
A diverse mix.
Yeah, and they added synthetic data too, like GLAN and MathScale, to really hone its reasoning and ability to follow complex instructions. They even specified the chat template used.
Any weird optimization choices during SFT?
A couple of interesting things. Instead of averaging the loss function across the training batch,
Which is standard.
right, they actually summed the loss. They found empirically this worked better for convergence for this specific 1-bit model. And consistent with pre-training, they found it benefited from a relatively larger learning rate during SFT compared to what you typically use for full precision models.
Again, different dynamics.
Seems so. And they also had to train it for longer, more epochs than you might expect for a full precision model of similar size to get the best results.
Needs more time to learn the fine-tuning.
Potentially, yeah.
Okay, so pre-trained, then fine-tuned for instructions.
Yeah.
Phase 3, direct preference optimization, DPO. What's that for?
DPO is a clever way to align the model with human preferences, making it more helpful, harmless, honest, without needing the complexity of reinforcement learning from human feedback or RLHF.
More efficient alignment.
Exactly. It works by directly using preference data pairs of responses where humans said, this one is better than that one.
So you don't need that separate reward model like in RLHF.
Correct. It optimizes the main language model directly based on those preferences.
Makes sense. What preference data sets do they use?
Primarily ultrafeedback and MagPi, both well-known public data sets containing human judgments on model outputs. Lots of diverse preference signals there.
And the DPO training details. Anything stand out?
It was relatively short, just 2 epochs. Learning rate was tiny, 2E7. They used a DPO beta of 0.1, which controls how much it can stray from the SFT model.
Okay.
And importantly, they used optimized kernels from something called the Liger kernel library to speed things up. The results suggest it worked well, improving conversational quality without messing up its core abilities.
All right. Architecture, 3-phase training. Now the moment of truth. How good is this thing? How does it actually perform?
This is where it gets really interesting. The evaluation results are, frankly, quite remarkable.
Yeah.
They tested it across a huge range of benchmarks, understanding, reasoning, math, code, conversation, the works.
And compared it against
Some of the top open-weight, full precision models in roughly the same size class. Think LLM 3.21b, Gemma 3.1b, Quen 2.58, 1.5b, models like that.
Okay, the current leaders in that bracket.
Exactly. And the first big headline is just the efficiency.
Right. The resource savings.
Absolutely. If you look at Figure 1 and Table 1 in the paper, BitNet b1.58 2b4t uses way less memory for the model weights themselves, excluding embeddings.
How much less?
Significantly less. And the estimated energy use during text generation is also much lower compared to all those full precision models.
That's huge.
They call it pushing the Pareto frontier, basically, getting a better performance versus efficiency trade-off than what was out there before.
So it's lean and mean. But can it actually do the job? How's the task performance? Can it keep up?
That's the kicker. According to Table 1, yes, it really can. It actually achieves top scores among those comparison models on several key benchmarks.
Top scores, even against full precision.
On some, yeah. Particularly in areas testing reasoning, general knowledge, math skills. On others, it's very competitive, very close to the best full precision ones.
So it's not just efficient, it's genuinely capable.
It seems so. While maybe one of the other models might edge it out slightly on average across all benchmarks, BitNet delivers really strong, consistent performance across the board, nearly on par with the leaders in its size class, but with those massive efficiency gains.
Okay, what about comparing it to models that were compressed after training? Like taking Quen and shrinking it?
Good question. They did that comparison too. They took Quen 2.5, 1.5b and quantized it down to INT4 using standard methods like GPTQ and AWQ.
INT4, so 4-bit. Still bigger than 1.58 bit?
Right. And Table 2 shows that while INT4 quantization definitely saves memory compared to the original Quen,
BitNet saves even more.
BitNet saves even more memory, yeah, because of that native 1-bit architecture. But more importantly, BitNet generally outperformed those INT4 quantized versions on the benchmarks.
Ah, so training natively 1-bit is better than post-training quantization, at least here.
It suggests a more favorable efficiency performance trade-off, yes. Better results at even lower memory cost.
And compared to other 1-bit models out there, how does it stack up?
They looked at that in Table 3, compared it to other near 1-bit models, some natively trained like Bonsai or Olmo BitNet, others post-training quantized like Falcon or Llama 3 variants. BitNet b1.58 2b4t came out clearly on top, significantly stronger overall performance than all the others in that 1-bit-ish category.
Wow. So it beat smaller native 1-bit models,
In respect, perhaps.
but also much larger models that were quantized down later.
Yes. Even beating quantized 7B and 8B models in many cases. It really underscores the effectiveness of their native training approach at this 2B scale.
Okay, it's efficient, performs well.
Yeah.
But how do you actually run it? Standard hardware isn't built for 1.58-bit weights, is it?
That's a critical point. You're absolutely right. The W1.58A8 scheme, 1.58-bit weights, 8-bit activations need special handling.
Your regular PyTorch or TensorFlow won't cut it out of the box.
Not efficiently, no. So the researchers developed and open-sourced custom inference libraries. You can grab the code, actually, at aka.msys.bitnet.
Okay, so they provide the tools.
Yeah.
How does it work on a GPU, a graphics card?
Since GPUs are optimized for standard types like 16-bit or 8-bit, they had to get creative. They built a custom CUDA kernel just for this W1.58A8 matrix math.
Custom code for the GPU.
Yeah, and they use this clever pack, store, load, unpack compute strategy because you can't efficiently store just -1, 0, +1 directly.
You pack them together.
Exactly. They pack multiple ternary weight values into single 8-bit integers to save memory bandwidth when loading from the GPU's main memory.
Okay.
Then, once the data is in the faster on-chip shared memory, the custom kernel unpacks these values back into a format suitable for the ternary math and does the calculation with the 8-bit activations.
Sounds complex. A workaround for current hardware limitations.
Pretty much. It minimizes data movement, which is key, but it highlights that current GPUs aren't inherently optimized for this kind of super low-bit stuff. Future hardware might change that.
Makes sense. What about running it on a regular CPU? That seems crucial for accessibility.
Totally. For that, they developed BitNet.cpp. It's an open source C++ library.
A reference implementation?
Yeah, basically a reference implementation for running these 1-bit models, including this one, efficiently on standard CPUs.
Does it have optimized code too?
Yes, it includes optimized kernels designed for common CPU architectures. They're tailored to handle the model's specific quantization scheme efficiently without unnecessary overhead.
And it gives accurate results.
Importantly, yes, it processes the weights consistently with how the model was trained, so you get numerically accurate results. It makes CPU inference feasible and reasonably fast.
So wrapping things up, it really feels like BitNet b1.58 2b4t is a significant step, a big leap towards making powerful AI much more efficient and accessible.
I think that's fair to say, absolutely. It strongly demonstrates that high performance at this scale doesn't have to mean full precision weights.
Opens up possibilities.
Definitely. And the fact that the model weights are out there on Hugging Face and the inference code is open, that should really spur more research and development.
People can build on it.
Exactly. Lowering the barrier to entry for experimenting with and deploying highly efficient AI.
And it sounds like the original team isn't stopping here. They're looking ahead.
Oh, yeah. The report mentions lots of future directions, scaling up to even bigger models using this approach.
A 7B or 30B 1-bit model.
Potentially. Also, co-designing hardware specifically for these low-bit models, making them handle longer text sequences, adding multilingual support, multimodal capabilities.
Images, sound.
Right. And just getting a deeper theoretical understanding of why this 1-bit training works so well. It's clearly an active research area.
Fascinating stuff. Really is. So thinking about all this, these big efficiency gains, it really makes you wonder, doesn't it?
How it might change things.
Yeah. How might the widespread use of models like this BitNet b1.58 2b4t actually reshape AI applications? You know, the devices we use every day or in places where resources are tight. That's